Okay, so in my mind, the way I think about this course, and actually, computer science education in general, we are sort of at a turning point here. In my mind, this is sort of the last week, the last topic we do that is learning more about C++. And the next topic, which is linked lists, is, as far as I can think of, I'm not going to tell you anything new about C++. I'm just going to be telling you about more programming techniques to use what you already know about C++. And that's pretty much true from now on. Like when you go on to CS 315, I don't want to say this is 100%, but almost everything you do is going to be not about more C++, but about learning techniques that apply in any programming language, right? So it's kind of a cool place to be, I guess. But the reason that I wanted to just bring that up is that you may find this topic to be sort of a bit of a catch-all. In some ways, it's sort of we're filling in the gaps. Okay, so the topics are going to be templates, which well, we'll talk about it. I'll just put the words up here for now. Exception, STL, and sometimes I also throw in, this is actually a subcategory of STL, I guess, but iterators. Okay, and those are, you could make an argument that those are sort of related, but they may seem like just sort of a hodgepodge from your perspective. I'm not sure. We'll see. Okay, so the first thing we're going to do is just talk a little bit about the standard template library. This is something, honestly, if there were anything that I thought maybe if I had to do it again, we should talk about a little more earlier in the course, this might be it. But the standard template library is a set of classes available for C++ programmers to use that act as containers for other objects. There's more to STL than this, but for now, to start with, let's think of it that way. Okay, so when I say to act as containers for other objects, hopefully that makes sense. We already have something like that, right? We've been using arrays, and arrays are things that contain other objects, right? You could also make an argument, sort of, that let's say a struct is something that holds other objects, right? It's made up of other objects. But in the STL containers are like that, but they're super, super powerful in comparison. So let me just share with you my favorite place to go if I need to find something out about the standard template library. I go to c++.com. And then reference, and then containers. Okay, so here's a list of all the different header files that contain these STL containers. Some of them contain more than one type of container. Most of them contain just one, I think. But here's one called array, and basically all this is it's just like an array, except it's gonna have some additional features. Okay, there's something called a forward list, which just means that well, it may be hard to understand at this point. We'll be talking about this more, but it's basically something that stores a list of items. And if you want to go through that list you can only go through it starting at the beginning and going to the end. You can't start at the end and then traverse it back towards the beginning. Here's a list where you can traverse it in both directions. You're probably thinking, what's the difference between a list and an array? We'll get there. So you can just see all these different options here. Most of them won't make sense. When I teach the data structures class, basically one way to think about the data structures class, 80 to 90% of it is just, we're going to go through each of these and study them one at a time, focused primarily on sort of what's going on behind the scenes. But so anyway, there you have it. What I'm going to do by way of introduction to standard template library is I'm going to focus on this one here called vector. Vector is an awful lot like an array. You could just think of it as an array, except with way more powerful, way more features compared to an array. As a matter of fact, let me just say that, you know, if you're out in the real world, you've got a job writing C++ code, you're probably not going to use an array. You're probably going to use a vector. We teach you arrays just because they're sort of more fundamental. You know, it's a little bit maybe like teaching you how to, you know, teaching you your times tables before we give you a calculator, right? Okay, so we're going to talk about vector. Just like arrays, you can have a vector of anything. You can have a vector of ints, you can have a vector of feet inches objects, you can have a vector of strings, whatever. Unlike arrays, you can always add something to a vector and not have to worry about resizing the vector if its capacity is exceeded. You can also, at any point, unlike arrays, you can just ask how big the vector is, or how many items are in it. That's just a couple of examples. So when you declare a vector, and I think what I'm going to do is I'm just going to put some code up here, as opposed to sort of developing it from scratch. So here is a program that uses vectors. I guess I would suggest staying with me as I sort of go through this one thing at a time, as opposed to sort of trying to take it all in at once. But so here's how you declare a vector. If you want a vector of ints, you put the word int in these angle brackets after the word vector, and then there's the name of your vector. Okay. One common way of adding items to a vector is with the push back function. So if I want to add something to the end of the vector, I just say v.pushback and I put an argument in there, and that gets put into the vector. So you could think of this a little bit like saying, if v was an array, I'd say something like v sub I, it's I. Well, it's I, right? Or something like that. Right? Okay, so, but the nice thing about pushback is if the capacity of the vector, if the vector is full, let's put it that way, the pushback function will automatically increase the capacity of the vector, or the size of the vector, so that you can add more elements to it. You don't even have to worry about what the capacity is. You don't care. Okay. I'm gonna digress just for a second here in case this clears something up for anyone. But as I'm talking about this, we're going to be talking about two different concepts of two different counts of things, right? when we dealt with arrays, often we would have the size of the array. For example, the array might be, excuse me, the array might have 1,000 elements in it, but then we might only be using 5 of those elements, right? And so we would have to maybe keep a separate variable called num items that would help us remember how many items are actually in the array. So hopefully that makes sense, the difference between the, I'm going to call it capacity, that's how many elements are actually in the array, as opposed to the size, which is our way of talking about how many of those elements we are actually using. So the rest of the elements are just junk or something. Any questions about that concept? Because we're going to have that same idea when we talk about vectors. You can kind of see here, right? There's going to be a size of the vector. That means how many elements are actually in the vector that we've placed in the vector. And capacity is going to be in its current state, how many elements could we possibly put in the vector? All right. Hopefully that makes sense. Maybe, and if it doesn't, and you don't feel like asking a question, maybe when we run this code, it'll make sense. Okay. So the capacity of vectors change as they're being used, right? So I can set the capacity manually by using the resize function, or also I can give it a size when I declare it. Like I could say this, whoop. Okay, that means declare a vector called v and start it off with a capacity of 100. Okay, or I can call a function called resize, which will specify the size of the vector. But like I said, if I'm using the pushback function, then I don't need to worry about how big it is anyway. So I want to talk about what happens if I call pushback, but the vector doesn't have any more room, right? So another way of saying that would be if I call pushback when size is already equal to capacity. Okay, when that happens, the vector is going to be automatically resized. And the C++ standard doesn't specify any sort of a formula or technique for how big to make the new vector. It just says you're going to have to make a bigger vector. So it depends on what system you're on, but one very simple and common technique is that if the vector is full and you want to add something to it, you're just going to simply double the size of the vector. Okay. So for example, if the capacity of a vector is 8 and you've already put 8 items into the vector, and then you call push back again, then the capacity of the vector is going to become 16. Okay, and hopefully it'll make, as we're talking about this, you'll be thinking, okay, we've done something like this, right? We when we wanted to store a string and we didn't have enough room in our variable, we had to delete that old variable, allocate a new one, and then copy the old one back into the new one, right? Not in that order, but we've done that before. This is sort of a similar thing that we're talking about here. We're gonna, what's going on behind the scenes, we as the client programmer, we don't have to worry about this at all. But what's going on behind the scenes is that there's a dynamic array. That dynamic array is gonna get, we're gonna have to create a new dynamic array that's bigger copy the old dynamic array into the new dynamic array, and then delete or deallocate the old smaller dynamic array. Okay. If that didn't make sense, it's okay. I was just sort of hoping to sort of, for those of you for whom that does make sense, maybe that'll give this some context. Can we change this out of vector directly aside from the declaration? Yes, there's a resize function. So at any point in this process, I could say v.resize 1200 or whatever, right? Okay. Okay. What else is going on here that you need to know? Let's see. There's a size function that tells you how many elements are actually in the vector. There's a capacity function that tells you what the capacity of the function is. In other words, of the vector, I mean, in other words, if you're looking behind the scenes, the capacity function tells you how big the dynamic array is that you are storing these elements in. We already talked about pushback. So the only other ones that I'm going to talk about, and you know, that if you looked at c++.com and got a list of all the functions in vector, I don't know how many there are, but there's a lot. Okay, we're just talking about 4 or 5 here. So there are 2 different ways of accessing an element in a vector. One is using the at function. One is using square brackets, just like you do with an array. Okay. The difference between those two is that at performs some range checking. So, and it's a little complicated. It doesn't do anything super nice if the array goes out of bounds, but at least it'll tell you. And it does something we're going to study later in this lesson, which is it throws an exception that you, the programmer, could then handle. Okay. With square brackets, it's just like an array. If you try to access something that's out of bounds of the array, it just tries to do it and sees what happens. Okay. Another difference between this and an array is that with vectors, you cannot use this notation to put something in the array, right? So in other words, you can't use this expression that I have highlighted there on the screen. You can't use that on the left side of an assignment operator. You have to find some other way of inserting things into the vector. Okay, so let's take a look at what's going to happen when we execute this program. We're putting the numbers 0 through 19 into the vector. Each time we put another number into the vector, we're going to print the size and the capacity of the vector. So this will be interesting because we'll get to see what happens when we try to push back when the vector is full, or when the capacity of the vector has been reached. Then when we're done, we're just going to call this function named print. Print is going to go through the vector twice, once using the at function and once using the square brackets function. Okay. So let's try that. To get to hold on. Templates, jeez. Okay. Definitely should have used shorter names for everything. Okay, so here's our output. You can see we start off by default, when we declare a vector and we don't indicate the size, it starts off with a capacity of 1. And because we called pushback once, the size is 1. Actually, to be really technical here for just a second, this program doesn't actually tell me what the default size of the vector is, right? Because I'm not printing out the default capacity, because I'm not printing out the capacity until after I have called pushback once. So I'm not sure if the default capacity is 0 or if it's 1. We could find out, I guess, if we just call it once before we get to the loop. Sorry, I'm just curious now, so I'm going to do this again. Okay, so apparently the default size is 0. So when you declare a vector and you don't specify what you want the capacity to be, it's going to be 0. So then when I put my first item in, that vector is resized to 1, right? Now when I go to put my second item in, the size of the vector is doubled to 2. When I go to put my third item in, the size of the capacity, sorry, I keep saying the wrong word. The capacity of the vector is doubled again to 4. Now you can imagine that, typically when you're using a vector, you've got lots of items in there. So you're not constantly resizing it every time you add something or take something out of it. But so, just as another example up here further, if I have 16 items in my vector and the capacity is 16, and I call push back, then what happens is the capacity gets doubled to 32. Okay. Any questions about this output? This should be clear to everyone what's going on here. Anyone want to ask a question? Okay. The next thing I want to talk about is something called size type. And size type is something that students sometimes struggle with understanding sort of the rationale behind it, but it's super, super, super simple to just use. And so at this point in your programming career, I would recommend just use it, because that's what people do, okay? So every class, I guess I should rephrase that. Typically, in the standard template library, almost every class has a type defined in it called size type. And let me make this bigger. That's not how to do it. Okay, so what that means is if you're a client programmer, so in other words, you are declaring a variable of type vector or list or forward list or any of those types that we saw that are in the standard template library, and you want to declare a variable that's going to represent the number of items in a vector or whatever type you're using, instead of using int, you're going to use size type. And the way you're going to say it is something like vector int size type. Okay, because size type is a type that is declared inside the vector class for you to use. So if you just say size type, C++ isn't going to recognize that. You have to say the size type identifier that was declared in the vector class. So just to see an example of how we should be using this in our program. Okay, Current size is keeping track of how many items there are in the vector, right? So instead of creating it as an int, I'm going to create it as a type size type. And then down here in print, I do it a couple times, right? I've got a variable I that is going through up to the size of the vector. So I need to make that a size type in both of these two forwards. Okay, so let me try to give you a little bit of a rationale behind that. You know, like I said, the only rationale that I'm really concerned about that you understand is that it's just the right thing to do, okay? But let me state the rationale in two parts, okay? There's sort of two parts to it. First of all, this makes it so that there won't be any mismatch between the type that you use for a variable that is storing a size as opposed to the type that the class is using. For example, in this statement right here, current size gets v.size. v.size, you don't know whether v.size, the size function returns an int, or whether maybe it returns a short, or maybe it returns an unsigned int, or maybe it returns a long int. We don't know, right? We can't just assume that it's going to return an int. So if I make current size an int, but the size function is returning an unsigned int, then I'm going to have a mismatch there on the assignment operator. Okay, let me just take a step back for a second here and say, in this class, we have not talked very much about the different options that you can use instead of int. So if you have no idea what I'm talking about there, that's okay. You can think of it as I'm telling you this for the first time, right? In C++, there are a variety of different types that we can use instead of just int if we want to. And I just listed off a few of them. And that's, at this point, that's all I really care that you understand. So that's rationale number one. We're going to make sure that, so the standard template library says, okay, in order to make sure that the client uses the correct type for its variables, I'm going to provide this type called size type. And so the client can declare its variables to be of type size type in order to make sure that the types match. Part two of the rationale is, on any given system, it's not guaranteed that a variable of type int or any other integer type will be big enough to represent the number of items in a container, right? So that could be a problem. If you have a huge number of items in a container, your counter variable, or your variable that's storing the size of the container, may not be able to store the size of the container. So the size type that is provided by each standard template library class is guaranteed to be able to represent the maximum number of items that the container can hold. Okay, so that's provided by the system, and then the STL class provides that to the client so that they can use that. Okay, that's all I'm going to say about that. It's also stated pretty much exactly the same way in the lesson. The main thing is just to know about it so you understand how to use it and you understand what's going on if you see it in somebody else's program, okay? Any questions about size type? So basically this program is exactly the same as the one we just saw, except instead of int, I have size type in these three positions here, okay? Any questions about size type? Okay, the next thing I want to talk about is something called an iterator. So the question is this because the largest int is somewhere around 2 million? Yes. Well, I mean, so I guess I would say yes. It's because I think what you're getting at there is the largest int isn't really all that big, right? Um, so I guess my answer would be yes. The reason that we have to do this is that the size int is not all that big, right? Not always big enough to store the number of items in a container. Hopefully, I guess the short answer to your question, I guess, is yes. Okay, so we're going to talk about iterators. Okay, so the deal here is, so in a vector, let's say that we want to traverse the entire vector and do something to every element in the vector. Okay, so that could mean print every element in the vector. That could mean multiply every item in the vector by 3. Could mean add up all of the items in the vector, or it could mean get the average of all the items in the vector. Whatever we're doing where we need to go through every element in the vector. Maybe we're searching for a particular item in the vector. So in a vector, that's very easy to do, right? We can just do it the same way we do with an array. That's what I did in the program. This looks an awful lot like exactly, especially if you do this one, right? In this one, this is exactly what we would do if it was an array. The problem is that most of the other containers in the standard template library don't have this very easy way to traverse the container. The nice thing about vectors is that you can directly access any element in the container. With most of the other containers, you can't do that. There's special rules for how you have to access the various items in the container. The reason for that is that it makes things more efficient in some cases, or you can add other features that you can't add to containers that work like vectors do. So the way to resolve that problem is that in C++, all of the standard template library containers have a standard way that you can traverse through every element in that container. And the way that you do that is you declare something called an iterator, and then you can make that iterator point to the first element in a container. You can make that iterator point to the last item in the container. That's not technically quite right, but I'll get to that in a second. You can tell the iterator to advance from the current item it's pointing at to the next item that it's pointing at, and a few other things like that. Okay, so what I'm going to do is I'm going to show you now how to write the print function using an iterator instead of using indexing, which is what we've done here, right? So, but first, let me see here. So I'm gonna get rid of this for loop for now. And what I want to do is I want to, underneath this for loop that prints out, that traverses the vector just using indexing the way we're used to, I'm going to type the analogous for loop that we would use if we were using iterators instead. Okay, so let me just start by saying that iterator is sort of a high level concept, right? It's more of an abstract concept. When you're looking at iterators, hopefully you can sort of be thinking to yourself, okay, this is sort of a high level thing. There is stuff going on under the hood here, right? Behind the scenes. So it's not really like I'm introducing a new C++ syntax. It's more like I'm introducing a high level operators that you can use, operators and functions. So first of all, iterator is a type that is declared inside the vector class. So in that sense, it's similar to size type, right? You can see the syntax here is pretty similar, right? So in this case, I is a variable of type size type. In this case, I is a variable of type iterator. And let me just point out, so as I do this, there are going to be 5 different steps involved in iterating through the container. So first step is declare. Okay, so with the normal way of iterating through an array, we declare an int. With using iterators, we declare an iterator. Okay, so that's the first sort of difference. Second difference, or second step, is we need to initialize that variable that we just declared. Okay, so with indexing, we initialize it to 0. With iterators, we initialize it to printme.begin. And that's just a function. This function returns an iterator that's pointing to the first element of the vector. Okay, I'm going to use the term pointing when I talk about iterators. I just want you to know that that doesn't mean it's a pointer, right? I'm just using that term in a more general way. It's an iterator that's pointing to or referring to or the first element in the vector. Okay. Third step in both of these, right? These steps that I'm putting down here apply to both for loops. The third step is compare, right? So when I'm doing it with integers and indexing, I compare I with the size of the vector. Keep in mind, something interesting about this is that I'm saying less than because the size is always 1 more than the index of the last item in the vector. Does that make sense? That's super critical. Should make sense because we've been using arrays for a while now, right? So let me just say it again. The size of the vector is always going to be 1 more than the index of the last element in the vector. You could say that same sentence with arrays, right? The size of an array or the number of items in an array is always 1 more, well, than the index of the last item in the array. Anybody want me to talk more about that? Because element is no, there's no null characters going on here. Okay, that's C strings. But when I declare an array of size 10, the indices are 0 through 9, right? So the size of that array, 10, is always 1 more than the index of the last element. Everyone clear on that? That's a super, super important concept for any of this to make sense now. I'm going to type that out. The size, and I'm going to use array, but just keep in mind that vector, the same thing applies to vector, right? The size of an array is equal to 1 more than the index of the last element of the array. Okay, so again, if I have an array of size 10, the index of the last element is 9. Okay, so That's why we say keep going as long as I is less than the size of the array. Okay, so in order to do the analogous thing with iterators, the creators of C++ said, okay, we're going to make the end function return an iterator to the one element past the last element in the vector. Does that make sense? In order to make it so that I can do the analogous thing here with my two for loops, the end function isn't actually an iterator to the last item in the vector, because that would make this wrong, right? That would make this stop too soon. So the end function actually returns the element one past the end of the vector. Okay, so that's how I do the comparison when I'm using an iterator to traverse a vector or any STL class. Okay, then we have I++, which is really interesting, right? Because I isn't an int, it's an iterator. So you can imagine that inside the vector class, there's an iterator class, and it's got a begin function in it, and it's got an end function in it, and it's overloading the increment operator so that when I say I++, what it's doing is it's making the iterator advance one element forward in the container. Okay, so when you see this, you think of it as, okay, that's a nice, convenient syntax to use because it's very similar to what we do when we are using indexing. But what's happening there is not actually indexing. What's happening there is I am advancing the iterator. Okay, so that's the fourth step, advance. Okay, and then the fifth step is access. I need to access the current element of the container. So when we're indexing, we just use that. We just do that by using the square brackets and putting the index inside. Okay, and this is super interesting, right? Because up here, we were sort of treating the iterator as if it was an int when we say increment, right? Now we're sort of treating the iterator as if it's a pointer, and we're dereferencing the iterator. So star I means give me the element that the iterator I is, quote, pointing at, unquote. Okay, so basically what they've done is they've made it so that we get to use the syntax of whichever types seems the most convenient at any particular point. Right here, using integer syntax is simpler and more convenient. Here, using pointer syntax is simpler and more convenient. Okay. All right, so I think I'm done with that. Let me just show you this in a, let's see, do I have this? Yeah, let me just show you this in a complete program now. So you can see here, I've just replaced the for loop that we had before with a for loop that uses iterators. Okay, and so one of the programs in your assignment, you will be doing exactly this, like almost just copy and paste. So let's just run this. So whoops, so we can see it in action. Not doing this very efficiently. Vectors with iterator, and I want this. So let's, I don't want this. So nothing changed, right? Just wanted to show you that it actually does work. One thing that I forgot to mention, super simple, but just so you know, you always have to do a # include if you're going to use STL container, right? Okay, anyone want to ask a question about iterators? Okay, and again, the nice thing about iterators is it's exactly the same syntax regardless of which STL class you are using. Okay, the next thing I need to talk about is, let's look at this parameter, right? We've been passing objects as parameters for a while now. So there's something about this that should look wrong to you. Anybody want to tell me what I'm talking about there? If you turned this program into me, I would say, hey, you're missing something on that line. So yes, that is correct, const, right? This variable print me is not changing inside this function, so it should be const. Okay. Oh, I'm sorry. Yeah, that is correct. So the problem with that now is going to be that this iterator I, C++ is not going to let you assign it to printme.begin because then I could use I to modify what's in the vector, and that would be violating my const. Okay, so if I run this right now, what's going to happen is, if I compile this right now, I'm going to get some errors, right? No viable conversion from something to something, right? Basically, the problem is that, oh, for one thing, I didn't put it in my prototype, but the problem is basically what printme.begin returns, because printme is const, it doesn't return an iterator because an iterator can be used to change printme. What it returns instead, if printme is a const vector, the begin function is going to return something called a const iterator. So now that we put const up here in the parameter list, as we should, if we're going to assign an iterator to the begin function, we have to make it a const iterator, and that looks like this. Okay, just make I a const iterator instead of an iterator. That makes it so that I can no longer use I to modify the contents of printme. So now I still have errors. Oh, I didn't save it. Still something wrong. What did I do? Print. What? Oh, that I have it hiding down here. Okay, I like this at the top. Oh, having a little trouble here. Let's see. We get this. Didn't save it that time. All right, I will get this. There we go. And run it. Back to my old output again. All right. Any questions about const iterators? All right. So as you can imagine, I'm just sort of scratching the surface here with iterators. if you look in the textbook, you're going to get a lot more information about them. There's different categories of iterators in C++ that vary according to what you can do with them. So for example, in a vector, the iterators are called bidirectional because you can increment them. You can also decrement them. In the forward list class, iterators are one directional. They are not bidirectional. You can only increment the iterators. You cannot decrement them. So we're not going to go into a lot of detail with that. I just want you to know sort of the basic fundamentals here. And all of the functions that we've talked about today operate on any kind of iterator, so you don't have to worry about that. Okay. All right. I think we have enough. Hold on. You cannot increment iterators. You can only decrement them. Well, in our function, we're incrementing them, right? Here's where we increment our iterator. So you can increment them. We've demonstrated that. But there are there's another, like if I was not using the vector STL class, if, for example, I was using the forward list STL class, I don't know if you guys remember that, but it was in our list over here, the forward list STL class. If you're using the forward list STL class and you declare a variable of type forward list iterator, right? So that would look something like forward list int colon colon iterator something like that. This iterator, you cannot use the decrement operator, you can only use the increment operator. Right, so I don't expect you to remember that. I'm just illustrating that different STL classes provide different categories of iterators. Okay, it's very possible that I said it wrong before. Iterators allow co-portability when working with some other container type. I'm not sure about that. I'm kind of thinking no. I think the main motivation is simply that it makes it easier for programmers to use, right? Because it's always going to be the same functions. I mean, I guess the only thing I can imagine is that if you had some code that used a vector and then you decided you wanted to use a list instead, there would be fewer changes to it. So that sort of makes sense, I guess. That would be another advantage. But I think the main point is just to have a consistent syntax between the different containers. So you don't have to like learn a different syntax for each new container that you use. Okay, so I'm basically done now talking about that first topic of using STL and iterators. We're going to talk some more about STL and iterators as we move forward here, but it's going to be more from the side of how you would create iterators and containers yourself, right? Because all of these containers, you can go look at the vector, the file named vector. It's a file sitting on your file system someplace. You could go look at it and you could see that there is a class declared inside the vector file named vector, right? And so there's iterators defined in there. And so basically the rest of this, most of the rest of this lesson is going to be talking about, okay, how can we get on the other side of this now and actually create our own container classes? Okay. So in other words, we are going behind the scenes now. So the first step towards that is to talk about something called a template function. A template function is a function that can operate on variables of different types. So in other words, the parameter, I don't have to say that the parameter is of type int. I can say the parameter could be of any type, and then I will make the function work for that particular type. You can see how this is related slightly, at least we're moving in the right direction, right? Because you can imagine that the vector class, the way the vector class is created, it can be used with any type, right? It can be used with int in here, but I could put string in there, or I could put feet inches in there, whatever, okay? So we're moving towards being able to do that, but we're starting with just simply a function, being able to work with different types. So let me just throw up an example here of what I mean. We're going to start with just a simple program that creates an array of integers and sorts them and then prints them back out again. Okay, so here we go. This is nothing more complicated in this program beyond just arrays, right? Which we studied in week 4. I am creating an array of ints. I am filling up the array. There's 25 items in my array, putting numbers between 1 and 1,000 in the array. Then I'm going to sort them, and then I'm going to print them back out again. By the way, the reason I'm showing you this is just a starting point, and then we're going to create a templated function from this. So here's my sort function. This is basically copied from lesson 9, the lesson on arrays. We're not concerned about the details here of the sorting, right? This is another function to support the sort. And that's it, right? Anybody need to just stare at this a little longer? Really, I don't even care what's going on down here. I just need to know that this is some code that sorts a list, sorts an array of integers. Okay, so here's what I'm going to do. I'm going to make it so that my sort function can actually sort an array of any type. So the way I do that is just above the function header, and technically this is going to be part of the function header, but the convention is to place it right above. I'm going to put this weird syntax. This is called the template header. Okay, and what this means is that, okay, in the following function, you're going to see a T somewhere, and you're going to determine what T is. T is a type, okay, and you're going to determine what T is based on the argument that was sent. So I'm going to put T right here. And what that means is, okay, if this function is called with with an array of integers as the first argument, then T is going to be int. And I know that from now on in my program, in my function. Okay. If I call this sort function and the first argument is an array of, let's say, strings, then T is going to be string. And from now on, if I use T inside my function, the compiler knows, okay, that's string. Okay, so In this particular function, it turns out that we don't use the type anywhere else. So we just put T there and we're done. That's it. Okay. Typically, there'll be something going on in here where you'll have to use T. Like if I'm sorting an array of ints, and let's say I had to declare a variable that was of whatever type the array was, then I would have to use T inside the function. Okay, now the problem is that we call index of smallest and we send it the list, right? Which is not always going to be an array of ints anymore. So that means that we also need to make index of smallest into a templated function. Yikes. Okay, so just like we did with sort. And then T right here. Okay, so now what this means is all I did, and now my sort function can sort arrays of anything. Okay, so I have to also add these to my prototypes. Oh, same thing. And then just to get some test code in here, I'm going to add some more to my main function that creates an array of strings. So let's go here. You can see there's my index of smallest, there's my sort. But here I have, okay, I'm declaring an array of strings. Here is just, it's a little more complicated to try to get random strings into an array. I just create some strings of random length here. So these are just going to be a bunch of random strings that I put into the array. And then I'm going to sort those strings and then print them out again. Okay, so just to be clear, the point here is I have one single sort function. It can sort an array of ints. It can also sort an array of strings. Okay. Any questions about any of that? Let me just run it so you can see it in action. Okay, so you can see that the integers are sorted and also the strings are sorted. Okay. Let me just say a little more about this syntax. The word T that I have here, that's just an identifier. I can make up whatever word I want there. There's a pretty strong convention to just use uppercase T there. Everybody, all C++ programmers just sort of know that if there's an uppercase T, that means that it's a type. Sometimes it's called a type parameter, right? In one sense, you could think of this as being a parameter that instead of being a parameter that is a variable like usual, right? That's a parameter that is a variable. This is sort of a parameter that is a type. What type is being used here can vary. So, I have seen in some textbooks, they'll use a word like maybe object here or something like that to try to be a little more descriptive. And I get that. But at this point anyway, unless that catches on a lot more, I prefer to just go with the convention of using uppercase T for that. Yes, there's the code in main. Let's see, let me just look and see if there's anything else I wanted to say about template functions. I think that's it. The one thing that is sort of unfortunate about this example is that typically when you're using a templated class, you would need to actually use the type of that class somewhere in the function. But in our case, we are actually never declaring a variable of that type. So if let's say that instead of finding the index of the largest item, I just wanted to find the largest item. In that case, I would start by saying, let the largest item be the first item in the list. So I would say largest item gets lists of 0, right? So in that case, largest item would be a variable of type whatever t is. Okay. Unfortunately, in my example, I don't have any opportunities to use that. So there's just an example of what that would look like if you do. Okay. Any questions about template functions? Basically, what we're going to do on Wednesday is we're going to talk about something that's actually much more powerful than this, and that is being able to write entire classes that can work with any type of element. Okay, so I can have a vector of strings or a vector of ints or a vector of feet inches or whatever. Right, so that's you could think of that's in main, right? So the whole point. So how does how does the compiler know you are using that template? It looks like you just used 2 different lists, and lists are a defined type. Okay, so right here I declare an array of, because this is no, it doesn't have anything to do with being in the same file. Right here, that's a good question. Let's see if we can work that out. Okay, right here I have an array of ints. Okay, and then I call sort, and the first argument is an array of ints. Right? So when I get down here to my sort function, the compiler is going to look at this and say, okay, the first argument was an array of ints. That means t must be an int. And so I'm going to have to, the compiler actually creates a function like this, except with where the array, where that first parameter is actually an array of ints. Yes, that's exactly right, William. Yeah, and so maybe just to tell you a little bit of what's going on behind the scenes that may actually help. When the compiler compiles this code, it's actually going to create a separate function for each different value of t. So in the compiled code, in the executable code, there's going to be a function called sort that takes int as its first argument, and there's going to be a function named sort that takes string as its first argument. And the way the compiler does that is it looks to see how much, wherever sort is called, every time sort is called with a different type, the compiler is going to have to create an additional function so that it can handle arrays of that type. Okay, so I don't know if that helps understand what's going on a little bit or not. If not, that's okay. That was just a little peek behind the scenes in case that helps you understand this at the higher level. Okay, so I will see you on Wednesday, and we'll get to talk about templated classes then.